The rover found organic molecules on Mars, the chemical building blocks of every living thing on Earth. And that discovery made answering the question of life on Mars harder, not easier. That sentence should feel wrong. A discovery that makes things harder isn't supposed to happen. Not after billions of dollars, not after years of travel, not after the most sophisticated robot humanity has ever sent to another planet, drilled into ancient rock and found exactly what scientists were looking for. And yet, here we are. The robot succeeded. Science is stuck. Here is the one question the Perseverance rover was built to answer. Is there evidence of ancient life on Mars? Not current life, not little green things walking around. Ancient life. Microscopic, long dead, maybe 3 billion years gone. The kind of life that would have left chemical fingerprints behind, the way a campfire leaves ash even after the fire is out. Scientists designed an instrument capable of detecting those fingerprints. They pointed it at Jezero Crater, a dried-up lake bed, a place where water once sat still for millions of years, the kind of place life tends to congregate on Earth. They drilled, they analyzed, and the instrument found organic molecules, carbon-based compounds, the same chemical class that forms the backbone of every living cell on this planet. The headlines ran immediately, "Building blocks of life discovered on Mars." Everyone assumed the next headline would be the answer. It wasn't. The problem isn't that the rover found the wrong thing. The problem is that organic molecules aren't proof of life. They're necessary for life. You cannot have biology without carbon chemistry. But carbon chemistry happens without biology all the time. Volcanoes create it, radiation from the sun breaks down minerals and creates it, meteorites carry it across space and deposit it on planetary surfaces. Mars has all three of those processes running constantly, and has had them running for billions of years. Finding organic molecules on Mars was, if scientists are honest, nearly guaranteed before the rover even landed. The real question was always harder. Can you tell the difference between organic molecules that came from life and organic molecules that came from geology? The rover looked at the data and produced an answer that no one wanted. Not clearly, not from here, not yet. Imagine you're a detective investigating a crime scene. The room contains fingerprints, thousands of them, overlapping, smeared, degraded, some from the suspect, some from the owner of the room, some from every person who walked through in the last decade. You can confirm that humans were present. You cannot identify which human committed the crime. That's the situation science is in right now. The molecules are there. Something put them there. Mars has too many possible sources and not enough resolution to tell which one. And the surface of Mars has been actively making the problem worse for millions of years. The planet has no magnetic field protecting it from space radiation. The sun's particles, energetic, constant, invisible, pour down onto the Martian surface at a rate 5 times higher than what you'd absorb standing at the perimeter fence of a nuclear power plant on Earth. That radiation doesn't just pass through, it chemically transforms whatever it touches. Organic molecules that formed 3 billion years ago that might have once carried a clear biological signature have been scrambled at the atomic level, rearranged, broken apart, fused back together in new configurations until the life-made signal and the geology-made signal look identical to any instrument reading them from the outside. The evidence has been sitting in direct sunlight for longer than complex life has existed on Earth, and the sunlight has been rewriting it the whole time. Then there's the instrument's other problem, the one that happens when it's actually working. To analyze organic molecules in rock, the rover heats the sample to extreme temperatures, hot enough to vaporize compounds so they can be detected in gas form. But Martian soil contains a class of chemicals called perchlorates, reactive salts that are present in almost every sample the rover has tested. When those perchlorates get heated alongside the organic molecules, they react, they burn, they chemically destroy part of what you're trying to read in the same process you're using to read it. The instrument works exactly as designed.
The instrument is also partially consuming the evidence while collecting it. It's like trying to read a letter by setting it on fire and analyzing the smoke. You learn something. You cannot learn everything. And what you've lost is gone.
47 years before Perseverance landed, Viking 1 and Viking 2 touched down on Mars and ran life detection experiments. The results were confusing then. Scientists argued about them for decades. Some people still argue about them. The response to that ambiguity was to build better instruments, sharper, more sensitive, more capable of detecting subtle chemical signals. So we built them. We put them on Curiosity, then on Perseverance. The instruments got dramatically better. The ambiguity got worse. This is not a coincidence. Better instruments don't just detect more signal, they detect more noise. They show you, with much greater precision, all the ways the data could be interpreted. Viking's instruments were too blunt to see the full complexity of what was there. Perseverance sees it clearly. Seeing clearly is not the same as understanding clearly. And in this case, the sharper the view, the more the picture fractures. The only way to actually settle this, the only approach that gets past the radiation problem, past the perchlorate problem, past the instrument sensitivity problem, is to bring the samples back to Earth physically. On Earth, laboratories can use techniques 100 times more sensitive than anything that fits inside a rover. Specifically, they can look for something called molecular chirality, the directional twist in organic molecules. Here's what that means in plain terms. Living things are picky. Almost all amino acids produced by biology twist the same direction, like a screw that only turns one way. Geology doesn't care. Geological processes produce equal amounts of both directions mixed together. That difference, all one direction versus equal amounts of both, is one of the most reliable signs of biological origin that chemistry can produce. You can detect it, but the instruments needed to detect it reliably weigh hundreds of kilograms and take up half a room. They cannot go to Mars inside a rover the size of a car. The samples have to come to the instruments.
The Mars Sample Return mission is supposed to do exactly that. Perseverance has already done its job. 43 rock cores sealed in titanium tubes sitting on the Martian surface right now, waiting for retrieval. The best physical evidence ever collected from another planet, sitting in a parking lot 225 million kilometers away, unread. The retrieval mission, a spacecraft that lands, picks up the tubes, launches them into Mars orbit, and transfers them to a return vehicle headed for Earth, won't happen before the late 2030s at the earliest. That estimate assumes the funding holds. The budget has already been cut. The timeline has already slipped. If you're alive today and you want a confirmed, definitive answer about life on Mars, you are looking at a wait of at least a decade, probably longer. And that's if everything goes right from this point forward. I want to tell you this ends with certainty somewhere close on the horizon. I genuinely do. The samples are real, the science is sound, the question is answerable in principle. It's just not answerable yet. And the gap between answerable in principle and answered in practice is measured in billions of dollars, in orbital mechanics, in congressional budget cycles, in decades of scientists waiting. The rover found what it was sent to find, and the finding revealed the limits of what a rover can actually tell us. That's not a failure. That's what real scientific progress looks like when it's being honest. It's slow, it's expensive, it's deeply unsatisfying, and it's the only method that has ever produced knowledge that actually holds. The question that Perseverance raised is the same question that haunts every attempt to find life in the solar system. Detection is easy. Confirmation is almost impossible. You can find a signal. You cannot always read it. You can find molecules. You cannot always know where they came from. You can build a rover smart enough to find the evidence and send it 225 million kilometers, and then discover that the last step, the step that actually answers the question, requires a precision that only works in a building on Earth. The smarter the tool, the more clearly it shows you what the tool can't do. The evidence is out there, sealed, waiting, and the key to reading it is on the wrong side of the solar system, with no confirmed ride home.